Yes, so this lecture will be more about NP-completeness, some variants of NP-completeness, and there are 5 topics. So I will I will finish what we started in previous lecture about circuits. I will prove that P is in P/poly, and this proof will be very closely related to the proof that 3-set is NP-complete. And then I will give a few more reductions, like important problems such as subset sum. I will prove that's NP-complete and Hamiltonian path. Then I will quickly say something. This is just a short point. What is strong NP-completeness, and mention a few problems. And then finally, I will say what's co-NP-complete. It will also be a short part. So most of the lectures will be the first 3 points. Okay, so let's recall what is definition of P/poly, and then prove that P is a subset of P/poly. So language NP-poly, if there exists a family of circuits that decides a problem for inputs, so each circuit decides a problem for inputs of length n, and the size of the circuit is at most polynomial in n. So L is in P/poly if there exists a polynomial P and a family of circuits C1, C2, and so on, such that 2 conditions are satisfied. The size of the circuits, so Cn, size Cn is at most P of n, and second, so for all x in 0, 1, for all bit strings.
And what is the rhythm in the ending of first of all? It's S. What is it? I assume that it is a family of circuits.
No, right.
No, in the first.
Yeah, a polynomial. Yeah, and this is such that C1, C2, and so on. Is it clear on the screen? I think so. A little bit small. I will write a bit bigger. I guess it's just clear.
And is it true that we can actually define not just P-poly, but for every class and for every function, like I don't know, NP-x or something like that?
So like P/x.
Yes.
Yeah,
or
I've never seen it, but I guess
yeah. /x, something like that.
Yeah.
But it's not useful yet, or find it in some cases.
Okay, and there was an exercise in last seminar, and it says that this class has another equivalent definition. It is problems decidable with polynomial advice, and the name comes from this definition. And what does it mean? So that means that there exists a Turing machine running in polynomial time that has 2 arguments, and for each input length, the first argument is a fixed string, and the second argument is the string that you want to decide. So the first argument is like polynomial advice, and the advice can be different for every length. But the size of the advice must be a polynomial. So polynomial time machine receives advice plus the input, and then decides the problem. But note that this number of strings that need to be decided is exponential. The advice is polynomial.
I'm going to write the AC and the FC are a part of P-poly.
Yeah, indeed. Because there is a third condition that the depth is bounded by, it's the same. Yeah. Okay, and so this is for languages over strings. But we can also have we can also define this for L over any alphabet. So any language over sigma. And how do we apply this definition? By just apply some bijective mapping to strings of constant length. So if you have a big alphabet, we map it to, and we can choose, it doesn't matter for this definition which mapping we choose because it's a constant amount of information to go from one mapping to another mapping.
We just basically encode.
Yeah, as bit.
Strings.
Yeah, as bit strings. And so there is, from previous definition, there is a special one I will use today, which was NC0. And these are circuits of constant depth with Fanon 2. So, okay. And so now here is a theorem we want to prove. P subset of P/1. Okay, so what does it mean? Well, we have to apply the definition. So we will take a problem, a language L and P, and we need to construct circuits. And how will it work? Well, we can think about our computer. So it's built from circuits, but there is a problem because circuits goes into cycles. After every clock step, the output somewhere becomes the input again. So it goes in cycles. So we need to break the cycles. So then think about your laptop, the CPU, and just put a whole stack of laptops on top of each other, each time giving the output to the next laptop. And so since it runs in polynomial time, you need to stack a polynomial amount of laptops on it. And then all the circuits together are just one big circuit without loops. And then the last laptop will give the answer. So let's say if the computation is finished, they just continue to give the result higher. It's a very intuitive way.
So we are replacing the parallel circuits by parallel laptops? Or?
Yeah. So laptops or CPUs or whatever you want to call it, and then just stack them into each other to avoid the cycles. And so you build a big circuit, and it's kind of real world intuition that it's possible. Of course, it's completely crazy to do it in such a wasteful manner, but we want to prove theorem. And the proof works exactly like I'm saying. So we will. Okay, maybe like a small mark you will get if you say this. So it's more than 0 you will get. Okay, and so but we will do the same. So we will consider Turing machine now, and it has a tape. It's the memory, and we will just layer by layer build a circuit. We will combine circuits that compute one step.
One step of Turing machine.
Yeah, one step of Turing machine. And so each time we copy the memory.
Well, but the input will be the memory before, and the output the memory after.
Yeah, afterwards.
And the transition.
Yeah, and one computation step can be done by NC0 circuit.
Yeah, it's basically.
Yeah, and so we do a polynomial of such layers, and we simulated all the Turing machine. Okay, let us go through the details, like how to encode the machine. So let's fix machine M, and so there is 5 tuple, a set of states. Then let's use the binary alphabet. Then there is a tape alphabet, a transition function delta, a start state, and some accept states. And so Turing machine at every moment it is located above itself, and you will see why I use big cells soon.
You can probably even say that the number of cells is finite.
Yeah, it's bounded by polynomial.
Yeah.
We only need to consider this is a very good point. So we only need to consider P of n cells, because after P of n, okay, let's say the runtime is strictly less than P of n. Less than P of n. So we fix n, but we also fix an input n, because we need to build a circuit for each input length. So here we consider P of n. So the runtime is at most P of n minus 1. So in the end, we end up in the last or earlier in the last state. Okay, and so at every moment the tape contains some symbol W3, W4, and so on. WP of n, and we will encode it as pairs. That's our plan. We will encode it in such a way that the computation head is close to the is next to the symbol that we are encoding. Okay, that sounds a bit strange, but it's easy to explain. We will work with pairs. So let us say that dash is not a symbol from Q, and we will encode each cell as the contents of the cell and a dash, except for the cell where the machine is located. And then if the machine has state Q, we write here Q. And then we have W3 and a dash, and so on. WP of n and a dash if the machine is not here. Okay, so this is
for each cell we have a pair, the word and dash
if machine is not there, and the state if the machine is there. So in other words, we will use the alphabet of our, so we will consider the states as a language over over gamma times gamma times Q union dash. So we assume dash is not in Q.
Q is conditions here.
Yeah. And so when one computation step is done, we get a new string. So for example, if machine writes W tilde and moves to the right, we will get something like W3 and then Q tilde here and more. So in this example. And so note, so at each moment we have a string that belongs to sigma p to the power n. And so the mapping, so it's clear, right? Every moment, so we can encode a configuration of a Turing machine as a single string of this form. And if there is one cell that does not have a dash in its second argument, in its second item, then it's a valid encoding. And now let us look, this is a mapping from sigma pn to sigma pn.
So every configuration is just an object for sigma pn, and the
one computation step
is just an
it's just a mapping from sigma pn to sigma pn. And so each cell can be computed by NC0 circuit. Why is it? So last time we said that NC0 circuit's constant depth is just any function that depends on so any NC0 function is a function that depends on at most finitely many inputs, and this is the case here. So to compute this cell, we just need to know the left cell, the cell above, and the cell at the right. So the left cell tells us the state in case the machine is here and moves to the right. The cell above tells us W3, and the cell at the right, well, if it's in a dash, then it doesn't do anything. But if the machine is there and moves to the left, it will tell us a new state. So we have a function that depends on a constant number of steps, but a constant number of cells, 3 cells. When each cell itself is just one symbol. So we have each cell is computed from finitely many arguments. Depends on finitely many arguments. And so this is NC0 circuit. We can build it with DNF formula like we proved last time. So a circuit like this.
We can use only 3 of them because each step is just moving the head left
yeah,
or right.
Yeah.
Okay.
But if machine could step 5 places, then we need a bigger and yeah.
How do we know if we need to move the position?
Yeah.
I mean,
so
you should
you
you need to access the state machine, I think. of the Turing machine? How do you do that?
Yeah. So to compute this state, there are two possibilities.
Yeah.
Well, three possibilities. Either the machine is not here and not here, then the state is just W3 dash. So there are case analysis. If you want to program it, we do a case analysis. So we look at the place and we say what should be here. Well, first case, the machine is one step to the left in the input.
Mhm.
And then we check if it's W2 and Q, we look in the table.
Yeah.
And if this is a right move, then we know that
Yeah.
QT, yeah.
And to look in the table, it is constant time.
Well, the table is fixed and we just need NC0 circuit. So to compute one cell, we have a fixed mapping. So in this construction, machine is fixed and then N is fixed. So we just have, it's a very boring circuit because we just repeat like all these times the same circuit. Just in the border, we have to be a bit careful. Okay. Well, let us say that if the machine goes left, then computation stops, for example. That's my favorite definition, but it's not the standard definition. Standard definition, if you go left in the beginning, then the machine stays on this cell and just goes to the new state and continues to compute. But for all purposes, I find this annoying definition because I need an extra case. It's nicer if it just falls off, but okay, that's my personal opinion. Let's not waste time on that. Okay, so we now understand that mapping is implementing one computation step can be done by NC0 circuit. And so now what is the circuit that we need in the theorem? It is a circuit that receives the input X and then maps it to an encoding of the input state, which is just like an X1, Q0 for the start state, here Q0, followed by, okay, it's kind of obvious. I probably should not write this. So then there is the last one, X. And then it's followed by blanks. And this is again NC0 circuit, such a mapping. So each cell is computed by a circuit of constant depth. And then we do this one step. And we do it P of n times. And then finally, we end up with some sequence 1W S1 till P of n S P of n. We need one gate to check whether the halting state appears, an accepting state appears, like AC0 circuit or something, like a check for every cell, which is a constant size circuit, and then a bit OR gate. So let's say AC0 circuit, and so in the end, we have answer. So X in L. And so here what we have is a circuit of size. So that's a good question. What's the asymptotic size? Yeah, so we have P of n is the bound on the time. So number of gates will be size bound by order, and it's, yeah, Pn squared. Because yeah, one step it is, so each cell of one, the number of cells is P of n. And then we have to do P of n times. And then the rest is smaller than P of n squared, assuming P of n is at least n, yeah.
Will we discuss how to encode these pairs in terms of graphs? So we have vertices of this. So how can we implement this?
So circuit is a list of gates.
Yeah.
Yeah. And then for each gate, it's a good question actually. Yeah, for each gate, yeah, it's always the same gate. So probably you would use two indexes for layer and so you just go one up. Okay, if you implement it, you need one index, but going from 2 to 1, it just with the quadratic function, yeah, it's a lot of work, but you know how to do it. Yeah. At least that's my experience. So students are at the level that they can figure out all this. Yeah. But we see that it's extremely boring circuit. The same circuit is printed all of the time. And it's incredibly important question. Because we not only prove that the circuit exists, it's also pretty easy to print out the circuit. And we need to remember this for our second task, that reset is NP-complete. And so here we have completed our first task. And we will see that we basically have completed 1/2 of our second task. Okay, so let's now start with this task. And I will, so reset is NP-complete. Remember what it means. It means for every problem in NP, we can build a reduction to reset. And I will do it using one step in the intermediate. I will first prove that circuit satisfiability is NP-complete. So what is this problem, circuit satisfiability? But I guess the name explains itself. So the input is a circuit. And the question is it satisfiable? So does there exist X such that C of X equals 1? And now the claim is that the reduction is precisely this mapping with small modification on the input. So let us go through the proof. So now,
well, can you explain again how the circuits inside is connected?
Yeah, so I will go into 2 steps. I will go from every problem in NP to circuit set, and then the second step is go from circuit set to reset.
So it's just reduction through this.
Yeah. And so now our problem, I will call it proposition because that's something that's less important than theorem. And so circuit set is NP-complete. So we fix a language, but now the language is in NP. And now we fix M. M is verifier. So polynomial time machine, and it gets two arguments. The verifier for L. Okay. And now I have to tell you what is the reduction. It means that I will fix for every X that might or might not be in L. So I need to print a circuit.
That means the rest of the previous proof, because when you
I will use the previous proof. So that's why I'm locally modifying the things. Almost everything is the same. So I have fixed the verifier. And now I want to know whether X is in L. So
and what is L again?
So I fixed a language in LP.
Okay.
Yeah. So fix a language L in LP and fix a verifier for it. Okay, let's call it V. That's easier to remember. But I'm not using the name, so actually, yeah. Okay, just to be sure, let's keep the name. And so what we have to do, we have to come up with a circuit so that X, okay, let us recall what means verifier. There exists a Y such that verifier accepts. And now we need to reduce it to circuit set. So we want a circuit. So, a circuit that is constructed using X as an input, and circuit is satisfiable if and only if X is in the language. So if and only if there exists Y, so that C of Y equals 1. And so it starts to become clear what we have to do. We need to build a circuit that simulates the verifier for the fixed X, fixed first part of the input. And the real inputs of the circuit will be the certificate part of the verifier's input. We need to build a circuit. It may depend on X, and the inputs are the string Y, and it has to say whether VXY accepts.
Again, we have a word from the language, and for it we have a verifier, and for verifier we want to build the circuit.
Yeah. So the reduction will map X, the input for L, to the input of this problem, which is a circuit CX. That's our reduction. And we want that X is in the language if and only if CX is satisfiable. So that's the definition of reduction, and we need to do it in polynomial time. And now everything is on the board. So what will be the circuit? Well, we will build a circuit for the verifier in the same way. But now we have to be careful. The input is a pair XY. It just has two parts. And so here we have some X's, then followed by some Y's, followed by blanks. And then we just substitute. And so we want to implement this mapping. And so the X part will be fixed. We fix X part in the circuit, and then this will be the real inputs of the circuit. So this will be fixed. So these inputs so we build our circuit. Then the first part of the inputs disappear because we fix them, and then the second part will be final input. And that's it. That's how we build a circuit. And we can do all this in polynomial time because the size of the circuit is polynomial, and it's extremely boring circuit. Each time the same gate is printed for most of the time, and the first and the last layer is also easy.
So for any NP problem, we build the verifier. We build for that verifier the same circuit that has size, that has polynomial size, and if
so once we fix the verifier, we know how to fix to implement this constant mapping, and then also the start mapping and this end mapping. So yeah, it's easy.
What have we just proven?
We have proven that circuit sat is NP complete. So this proposition, circuit sat. Oh, I say circuit is NP complete, but I meant circuit sat is NP complete.
And then basically, circuit sat is complete, then resat is complete just because of reduction.
Yeah, this reduction I still need to explain.
Well, but why it is so for every language in NP, we have a circuit which is satisfied.
Yeah, for every language in NP, for every language in NP, we need to map inputs of this language to circuits.
So we've just built a reduction from.
Yeah. That's definition of NP hardness.
Okay,
Sorry, okay, I should.
The surface variability in NP, it's probably obvious.
Oh, sorry, yeah. Because the assignment is certificate. Yeah, you're right. It's important for exam that you always say this silly thing. Of course, this problem is an NP, and now I forget myself. So now we prove that NP hard. Okay, and here I say what is reduction, X goes to circuit. And for each verifier, we can build such a mapping.
And what is written well when you build the mapping from X to circuit X? You have for every X in language, even on the CX or V, or what is?
CX is a circuit, so it has certain inputs.
Yeah,
But here I would call them Y.
no. The just a little bit upward than that.
So here,
No, a bit more upward. Next, yes. Here, CX of what?
sorry, this is some old thing. I didn't delete it. Yeah.
And what is
CX is satisfiable if and only if X is an R.
Okay.
Yeah, and X is a subscript because the circuit itself is a function of X.
Okay.
So this is very important proof. If you understand it, then the major goal of the course. Oh, sorry, not yet. We still have reduction from circuit set to tree set. Almost there. Okay, so now I need some the next goal. We've proven that circuit set is NP complete. Now we are interested in tree set, and so the only thing is this reduction. Reduces to tree set. Okay, and so recall what is tree set. The input is a formula in 3CNF that means a bunch of clauses of length 3.
No, more than 3.
Oh, at most 3, sorry, well, okay, you can say, you can repeat the same literal. It's a cheaty way to have exactly 3, but you need to be careful, but some people say no, they have to be different literals or different variables even, so there are several variants. Yeah, so again, very good remark. And so there is a problem called the very tricky problem. It's called to reset, where every variable appears at most 3 times, and every clause has exactly 3 different variables. And so not 3 different literals, but 3 different variables. But yeah, the same literal, both in negation is kind of stupid because the clause is always true. Yes, and this problem is in P. So because if a variable appears at most 3 times, and every clause has exactly 3 variables, three different literals, then you can build a matching between clauses and variables, and then you can set so you can make a clause true by choosing the value of one variable, and so you always get true. And it's kind of tricky place where people try to. So in the end, I've written some advice on how to find reductions. And the last one is, if all previous fails, try reset or some variant of it. And so people, they start to think, oh, okay, I can make a nice reduction if I know every variable appears at most 3 times. So they add it to the condition. And then if the size of the clause is at most 3, you're fine, it's NP complete. But sometimes people say, oh, it only works if my clauses have exactly 3 literals. So they add it to the reduction, but then they can't find the reduction because the problem is in P.
In P.
Yeah, NP,
Oh,
because
no.
it's trivial. Yeah, its answer is always yes. So, or you're lucky and you can build a reduction, and then you know that the original problem is also NP, and the answer is always yes. I can imagine it also happens to someone. So, yeah. Okay, but I should not funny anecdotes. I should prove why this happened. Okay. So now we prove that we can implement every function with DNF, but we can also do it with CNF. And that's useful for 3-sat. And instead of, so before for DNF, we were looking to the values where function is 1, we look to the values where functions is 0. So for every function, so F maps 0, 1, C to 0, 1. So let's write down the CNF. So the claim is that f of x is equal to, so we iterate over all z, for which f of z is equal to 0. And then we check whether the input is equal to z. So we take a big input. And so, okay, let me write it in pseudocode. X is equal to 0. And this we can write as a formula in CNF. Equal to 0. And it's, I don't remember it, but it's probably something like, sorry, Z1, X1, or Z X. So this is the clause. Let me check it. So if both X1 and Z1 are 0. So okay, so if X equals Z, we need to have all zeros. And then the value will be 0. That's what we have to prove, right? Fx is equal to this. So if both x is 0 and z1 is 0, then we have, so then the negation doesn't exist, and we got the 0 here. And if zc is 1 and xc is 1, we get not 1, which is 0.
So you have a negation into the power of z something.
Yeah. So if f of x is 1, it means that x appears here. In this, sorry, if f of x equals 0, it means that x appears among these z. And so we have to check what happens if here we have x1 and x1. And we know it's all 0. So the clause will become 0. But if x is different from 0, then it must differ some bit. There will be at least 1, 1, and the clause will become 1. So if f of x is equal to 1, it means x differs from all these here, and all the clauses will be 1.
This is not 3, so
no, but if we set c equal to 3, we are good. So we will need to replace circuits by a bunch of functions with 3-bit arguments.
wait a second. So we have the size of z is just equals to c, and for each c we have a circuit. Or
we have a formula.
Yes, but the length of the formula is c.
Yeah, and I will. I promise
different-
I will only use. I need to tell you what is the reduction, and I will only use c equals to 3. So we have nice 3 CNF formulas.
So we're
Or c equal to 2.
so we're forgetting about the all circuits which are more than 3.
No, I still need to tell the reduction. C is not related to circuit. It just I want to point to you that I can use. I will somehow use that for every that I have such things. for every function with 3 arguments.
No, I just missing the point. Well, the circuit sum is just, we have a circuit, but circuit, the circuit, we mean the family of circuits for each length or the circuit of fixed length?
I'm saying that for every function, I can use a 3CNF formula in my construction that evaluates the function. It's the only thing. I don't tell you the reduction yet. Reduction still has to come. I just say if I want the function, then I can evaluate its value using 3CNF. Okay, so now I will do more preparation. Yeah.
Why 3CNF? Why we can do any function in 3CNF?
No, for a function with 3-bit argument,
Yeah.
I can put in and same for 2-bit argument.
Yeah.
Big arguments we can get to see.
Yeah.
Yeah.
Okay. And so what are the functions I will use? And they are indicator functions that says that a certain variable xi is equal to xj and xk. So it's a kind of so this indicator function. This is equal to 1 if this equality holds. It's 0 if this equality fails. So this is a function of 3 arguments. Okay, sorry, let's write A, B, and C. Why use English? So we have a function with 3 inputs, B and C. And so, for example, if A equals 1, B equals 1, and C equals 0, then the value of this function is 0. Right? Because we have 1 equals 0. And so we can make that, but 0, 1, 0, that's correct 1. That will be evaluated to 1. And we can do the same for OR. And we know that we can evaluate this using 3CNF formula. Check correctness of equality using A equals to B or C. And then the one A equal to not B. We have 3 formulas in 3CNF that tells us whether equality holds or not. Okay, and now I think you can guess how we can map circuit to a formula. Okay, no, maybe there was one clever idea missing. So what will we do? Let us look at a circuit. Okay, maybe a stupid one, but doesn't matter. Let's take another pen. Yeah, also not so good. So here is x1, x2. Let us say this is N, this is OR. Okay, it's probably a stupid circuit, doesn't matter. So what is the idea? We have a circuit and we want to know whether we can give it variables. So we will create, for the formula, we'll have more variables. We will make a variable for every gate. So this is x3, x4, x5. Okay, and now the formula will be as follows. So circuit will be mapped to the formula x5 and then we will check whether the output, so x5 is the output. We want it to be 1. So we require in the formula it's equal to 1. And then we check whether all the gates are correctly evaluated. So we check whether x3 is equal to x1 and x2. And then x4 is equal to x1 or x2. And finally, x5 equal to x3 or x4. So that's our formula. So that's how our reduction works. And here we have a function that we can implement with 3CNF using this technique.
Well, but you have x5 pixels, x3, and x1.
Oh, sorry, the mistake. Yeah. Like,
Okay, we can transform. No, not five, three, sorry. This is for binary circuits, but I mean, each gate has only two input
Yeah.
edges, but we can transform.
yeah, good point. Okay, so first step, transform fan in to circuit. Fan in two, and then second step is this construction. And that's it. Very good. Okay, now my last marker. Well, I still have other colors. Okay, and so now let us check that. So that's a reduction. Clearly, we can build it in polynomial time. And now let us check equivalence. So if circuit is satisfiable, we can find x1 and x2 so that the output is equal to 1. And that will be the value of our variables here. And so here, the input of the formula has 5 inputs, and we just set it equal to the values of the gates. And then all these checks will evaluate to correct, because that's how we build a check. They verify whether the output of the circuit is computed correctly. So circuit satisfiable, then this is satisfiable. And if this is satisfiable, then we know how to choose the inputs, and all the gates will be computed correctly. So in both directions. So this is satisfiable, then this is satisfiable, and if this is satisfiable, then this is satisfiable. And so we are finished. So we proved that circuit sat, that tree sat is NP hard. And obviously,
But it isn't the proof which Cook and Levin gave. No, it's just.
well, Levin gave all this in 2 lines because he found it obvious. And I don't know which proof Cook he gave. I think he made their direct construction.
But you said a couple of questions ago that.
In Sipser book, there is direct construction. So they go directly from Turing machine to formula.
Oh, so,
And this is messy.
but
Yeah.
you're using the Levin construction, but Sipser is not.
Well, I use same construction as Aurora Barak and recent books. But I don't know about original Cook paper. I didn't check it. So yes. And I was just saying, obviously, 3SAT is an NP because assignment is certificate. And so it means 3SAT is NP complete. And so we have finished the second goal. Okay, and so now we will do a few more reductions. So hopefully in the next 20 minutes. And then I can give a few definitions in the last 10 minutes. Okay, so let's delete everything. And the next task is to prove positive 1 and 3 set. And we will do it. So now we will prove that these 3 problems are NP complete. And then I've done enough reductions in class. There are a few more reductions in the seminar. Okay, so and it will go by reduction from 3 colorability. So that's given a graph, can we assign one of a color to each node, and we can use 3 colors R, G, and B, so that no edge connects. So every edge connects nodes of different color. But by the way, prove that 3SAT is NP complete is connected to a real programming experience. Like when you have a hard problem, you can, in practice, it's often reduced to 3SAT solver. And so like mini-SAT in Python, or Python SAT, the package is Python SAT. Just like the basic package, it works pretty good. Like even if you have 1,000 variables or something, or 10,000, You can get answer within the second. And so what you're doing is you take whatever problem you're working on and you transform it to formula and tree set. And usually you can do it quite quickly. It's not so difficult. So you don't need to go through this proof. That's also what the proof does. But the proof tells you it will be always possible to go to have an efficient reduction to tree set. So, well, okay, if the verifier runs in time P of n, we get P of n squared, but this square is actually not needed. But it's kind of tricky proof. I'm not going to teach. It's an Aurora Bara. Okay, but in practice, the reduction is really easy. Almost always it's easy. Like you just look at constraints, turn them into, okay, enough philosophy. So has anyone done this once? So no? No. And then you don't learn this somewhere in the software course.
But the transforming into set?
Yeah. Problem and like vertex cover, it's just like you have a variable for every node, and then you have a bunch of requirements that for each edge, one of the two endpoints needs to be set to true.
Yeah,
It's very elegant.
I've built a couple of times something like that, but it wasn't pleasant. It's a messy.
Yeah. Some problems, then you need many indices and variables. But for some problems, it's like, so I'm doing something with the Huawei company, and there it was also a problem like the disjoint path problem. Like find two paths, it's a bit more complicated, but find two paths that are disjoint. And so, okay, and so the natural way is have a variable for each edge, and then check well, for every path and every variable we should have an edge, and then check whether no edge is used by both paths, something like this, and then you have no connectedness requirement and so on. Okay, so but I was talking again. I should write down tree colorability. Input is graph VE and you color vertices. Or at most 3 colors. The graph is bipartite and 2 colors work. And so now what is the positive 1 and 3 set problem? So the input is a 3CNF formula. So F and 3CNF. And the question, can you find assignment? Sorry, yeah. And all variables are positive. So no negations. No negations. And the question is find an assignment that makes precisely one literal in each clause true.
And we want to reduce the true color to that problem?
Yeah. So we want to, that's our new theorem, assignment that makes exactly one literal true in each clause. Okay, let's do a small example here. For example, X or Y or Z, and not X or not Y or not Z. So what is it, yes or no? The answer here. No. because answers here and here are opposite. So in one of them, you need to have two. But if I do like this, then answer is
What is the name of the problem? Something.
positive 1 in 3 sets.
And what do you delete it?
Yeah, now I deleted the negation here, so this
Oh.
argument doesn't work anymore. And now the answer is yes, because we said that z equal to 0 and x different from y.
And so we have only one.
Yeah. So here there is one of the two is 1 and one of the two is 1 here. Okay, so that works. Yeah. And so so let us start with the graph. What is the reduction? Well, we will make three variables for every node. Variable indicating that this node has the color. So we will have here, let's say AR, a B, and a G. And so here we have node B, we have R, C, D, and so on.
So A is just the colors and the.
Yeah. ER, and so on. ER, EB, EG.
So
And now,
the index of a vertex is a color.
yeah.
So in that example, all vertices are red.
Yeah. No. So here I'm lazy. So I just write down the names of all variables we have. And I'm a bit lazy, so I just say, for this node, the three variables are called B, and the subscript denotes the color, and so on. Okay, and now you can tell what is the equivalent 1 in 3 set clause. It's very natural one.
Well, we want that vertices which are neighbors to be the different.
Yeah.
Well, they need to be exactly one positive.
Yeah.
Positive variable.
Yeah. So I will use. So we cannot have that AR is 1 and BR is 1. So we will use AR or BR. So note it's exactly 1 in 3 set. So it means that 1 in at most 3 set, I should say. And so we cannot have both equal to 1, but we can have both of them.
No, but it's not or, it's so.
Yeah, but we need dummy variables. Sorry, there are more variables. So for every edge, we need a dummy variable. I will call the y, for example. Y DE, and here Y DC, and I need to add YAB here. So this is for the case that both AR and BR are equal to 0. Then we can set this one equal to 1. Okay, and so yeah, so this clause prevents AR1 and BR1 because then we have two ones.
So
But
why do we need the dummy variable?
it's for the case that both AR is 0 and BR is 0.
Why just not?
For example, if this is green
Okay.
and this is blue,
We would create it such way because we don't have solar in sun.
yeah,
We just implemented solar by them.
yeah. And so we do this for all edges. So for all, okay, let's do it more general. Let's call this UR, UV, and YE. So let's call it.
We need one dummy variable or 3 dummy variables for each edge. So we have.
Yeah, good point. So because we have 3 such things, but actually we only need 1 for it. Because only one of the 2 zeros can only happen in one case.
Okay.
Yeah, so it's a bit more complicated, but yeah, you're right. The easiest proof we have a 1 here, and then we do the same thing for UG or VG or VV2, and then UB or VV or YUV3. And we also need to enforce that there is exactly one color selected in each node.
And 1, 2, and 3 for Y is what is it?
Okay, let me do the reduction from beginning. So first we will enforce one color for each node. And so it means we will have VR or VB or VG. So here we make an N over all nodes. And so this enforces that for every node, exactly one color, one of the colors, one of these variables is set to 1. And then we enforce that no two neighboring nodes have the same color, which goes by this thing. So now I answer your question. So if so, for example, if this is A and this is B and they're both red, then we will have 2 1s here. And so it's not allowed. But it can happen that this is red and this is blue. Then we have exactly 1 here. It can also happen that this is blue and this is blue, this is green. And then we have 2 zeros here, which is a problem. Therefore, I added this third variable and we can set it to 1. This variable is only used here, nowhere else.
What does mean the second index of Y?
Because we need 3 copies of the variable. Your neighbor pointed this out and he was right. So we needed the same thing for the second clause, where we do the same thing for green and the same thing for blue.
So we just can name them.
Yeah, I could also call them.
Why UV red, why UV green, and why UV.
Yeah.
Okay.
You're right. That's a better name. And actually, we can use the same variable because the 0, 0 case will only happen in precisely one of these cases.
So if we have 0, 0 case, we just put
this variable to 1. So that's the idea of construction. Now I actually explained the proof already, which is a bit messy, but you are asking for it. So now I just explained the construction, but I mixed it with explaining why we do it. And this is because you are thinking too fast.
I get how we compute why you are.
Well, in the end, we will rename the variables with indices if we use actual 1 in 3 set solver. I don't think it exists, but so we just need a bunch of variables.
No, I mean, how do we from the graph? How do we get why you are?
Yeah,
Without
I forgot.
knowing
Yeah, I
the
forgot to add it.
or-
Yeah. Sorry, and here also more and everywhere. Okay, so that's.
Now, how do we know why you are without knowing the solution?
No, they're just variables. We need to create a 3-dot formula.
I
Yeah,
get.
yeah. They're just variables that are used only once.
Yeah.
And therefore I need all these names because there are so many of them.
No, that's,
Yeah.
okay.
Okay, so then let us go through the proof. So clearly we can write down this formula in polynomial time because the size is here. It is number of vertices plus 3 times number of edges. So that's the number of clauses, all of size 3, and it's a simple rule. We can implement it in polynomial time. And now we have to check its equivalent. So if coloring exists, then we set the variables according to the coloring equal to 1. And as we already explained how to choose the variables here, it just for every 3 edges, we have 2 cases. The 0, 0 case is set to 1, and the others to 0. And I already explained this. Oh, the blue is not so clearly visible. Let me check this marker. Oh, better. Okay. And then opposite, if we have assignment here, we can read out the coloring. And for again, the same sequence of arguments, we can not have 2 times an edge between 2 times the same color, because that would have 2 1s here in such a clause. Okay, so we have proven that this one is okay. And now let us go to subset sum. So there are no questions. So subset sum, we are given a bunch of numbers, and we want to find and a target number, and we want to find the subset of these numbers whose sum equals the target number. Okay, it's not really a set; it's rather a list of numbers, and we want to find a sublist that evaluates to 1. So,
So the multi-set.
yeah, multi-set subset sum. Input is let's say D, A0, sorry, A1 till AN, and they're natural numbers. And then the question, does there exist a subset of N? So this is the set 1, 2 till N of natural numbers. Remember from previous seminar, just to be sure, such that the sum of I and I, AI, is equal to T. So that's the problem. And now we want to reduce from positive now we have
So D is also.
yeah, T is also input. Now I'm confused. I want to write the other inequality. So I want to say that yeah, subset is harder. Yeah, that's right. So we want to reduce positive 1 and 3 set to subset sum. And this is nice proof. So so positive 1 and 3 set, it's a bunch of clauses. We have clauses 2 till Cn, and we have variables x1, and we need to come up with numbers. So here we have numbers, and let us first make a table. So if a variable appears in a clause, then we write 1. If it doesn't appear, we write 0. And so we have a second variable, might be 0, 0. And x3 might be 0, 1. Something like this. And so we continue. And so how do we map such an instance of positive 1 and 3 set? So just 1 and 3 set, it's a bunch of clauses of length at most 3. So and I just make this table, meaning that I write a 1 if x1 is in C1.
Okay, so the number of
Yeah.
ones in one column is
At
3.
at most 3. Yeah.
So it's just the indicator table.
Yeah, indicator table. And now to get these numbers, I will just interpret this as a number in base form.
One question.
Yeah.
What about negations?
Well, it's positive 1 and 3 side. Yeah. So, so I interpret this as a number in base 4. So this is right. 1, 1 is equal to 5 in base 4. Yeah.
What do you mean 1, 1?
Yeah, 1, 1 in base 4 equals 5.
And how that corresponds to 1?
So this is equal to 416 times 4 is 64 is 69. Just to be completely sure you understand it.
What do you do?
Explaining what means base 4. Because there was confusion, but sorry, it was not needed. Yeah,
Okay.
and I never know what's happening. So
How is it connected to our?
okay. So this will be A1, and this will be A2, and this will be A3, and so on. And finally, sorry, here, and will be equal to AN in base 4. And then we have finally our target, and it will be the number 1111 in base 4. That will be equal to T. And so now the reduction is finished.
We are trying to reduce
Yeah, this problem to this problem.
Oh.
We want to prove that subset sum is NP hard. Yeah, I forgot to tell, but I thought it was obvious. Okay, so now reduction is finished. So we can do it in polynomial time because we just have to compute these numbers in base 4. And this we take powers. It's very easy to do, especially in base 2. Right? So,
And why again the
so no, I just explained you was the reduction. I did not prove it yet.
no? But
So I first want to know whether reduction is clear, yes or no. So how to get these numbers?
how to get these numbers is clear. How
Yeah,
to
make the table. Okay.
No, but the last row, which is n+1.
Yeah, it's all ones.
Why?
So that's why the reduction works. I refuse to answer at the moment until I confirm that reduction is clear. I'm not making the same mistake before.
We don't need to understand why, how.
No, at this moment, not. In 2 minutes, you need to understand, but now not.
It's
Am I right that on each row there is 3 ones?
No, in each column, there is 3 ones because every clause has at most 3 variables.
Okay, okay.
Yeah,
Yeah.
okay. And that's why I choose base 4. Yeah. Now you love, but it's indeed obvious if you understand why. Okay, now let us check equivalence. So let us assume there is positive 1 and 3 assignment. And then if x2 is equal to 1, we will select it in our set I. So we select all the x's which are set to 1 in our set. Now let us look to the sum of these numbers. So here I selected A2 and from 1 here, and let's say xn is also selected. So I select this. So when we sum up these numbers, we get exactly all ones here, because we assume that there every assignment means exactly 1 literal true in each graph. So in every column, we will have selected precisely 1, 1. So by construction, yeah. So we have a 1 and 3 assignment.
Yeah.
Assignment makes in every clause exactly 1 variable true. We select these variables to be in that's the one who appear in our sum. We add them up, and that means in every column we have exactly 1, 1. There will never be a carry bit because we have exactly 1, 1. Okay, now the other direction. Imagine that there exists a selection of numbers so that we get the all ones, that we get their sum is t. Now let us verify there are never carry bits. Of course, they're never carry bits because in every column we have at most 3 ones. So even if we select all of the 3 ones, we can have at most a 3 here. We can never have carry bits. Okay, one more time. Imagine there exists a selection of numbers here whose sum is equal to t. I claim that from this we get an assignment that makes in every clause exactly one literal true. Okay, so let us look to this sum. And let us evaluate it from least significant to most significant. In first column, there cannot be a carry bit. Why? There are, even if we select all of them, there will be no carry bit in first column because there are at most 3 ones and we're using base form. And that means that, so of course, we will have, that means that since there is no carry bit, it means exactly one, we must have a 1 here by definition of t. And it means that precisely one of these numbers must be selected. Precisely one out of these 3 ones here must come from a number that's selected. And that means in clause Cn, precisely one literal is true. And the same is true for the second column and the third column and so on, because we never have carry bits.
I may write that we can take any other base that is larger than 4.
Yeah.
Well, what is the knowing and what is the conclusion? We claim that we don't have any carry bits, and that's why Cn have only one. One. Or
that's why among the selected nodes in the sum, there can be at most 1. If there are 2 or 3, we would have a 2 or a 3 here.
Yeah. And at most 1, 1, or no, exactly 1.
Exactly 1, 1. Yeah, sorry. Yeah. So it should mean, unless there are no questions, that subset sum is okay. And now let us look at the last one. Well, okay, I don't have time anymore. So I will skip Hamiltonian path. And let's quickly say the 2 last things what I have to say here. So strong NP-completeness. It means that it's about problems that have integers like subset sum. If problem, so here the numbers are given in binary. They're huge numbers. We are taking 4 to the power n for the most significant digits. They're huge now. So strongly NP-complete means that the problem is NP-complete even if all numbers are given in unary. So then, yeah, for clique, there was just this number that's bounded by n anyway. So if we replace n in binary by a string of n zeros, nothing changes. But for subset sum in unary is solvable in polynomial time. It's exercise for your seminar. So by dynamic programming.
The definition of
Yeah. So a problem is strongly NP-complete if it's NP-complete, even if all numbers are given in binary, in unary. All numbers, all integers are given in unary. Then the problem is strongly NP-complete.
It is NP-complete or NP-hard?
At the same, same. So it is strongly NP-hard. If it's NP-hard for all numbers in unary, it's strongly NP-complete, NP-complete for all, and so on. And so 2 problems that are strongly NP-complete, and I will not write it on the board to save time, but just look into the seminar. There is this problem 3 partition. This one is strongly NP-complete, and I forgot to write it in the seminar. That's stupid. Just remember the last one in the first list of problems, 3 partition. It is NP 3 partition And the proof is difficult. I mean, not so difficult, but it would take half of a lecture. I can. So it is strongly NP-complete. Okay, and the problem that's subset sum is in pseudo polynomial time. It means as in polynomial time if numbers are given in unit. And the last thing I need to explain is problem co-NP. So a language is in co-NP, so this definition. So language L over sigma is in co-NP if its complement is in NP. If minus the language is in NP. So and note that so three sets. So a problem is and okay, and what is co-NP complete? I think or co-NP hard. You can guess, right? So what means co-NP hard?
At the same, but
Yeah. If for every A in co-NP, the A reduces to L. That's another definition.
we would have to need to add the L over the sigma star or the sigma.
Yeah. So you need to say what is the complement. Okay, it's a formal definition.
Here, but you wrote L over sigma. But...
Yeah. I need to say what is the alphabet in order to say what is the complement.
Oh,
It's a formal definition, but like most people think about sigma to be 0, 1 binary languages. So okay, and co-NP complete. You also understand. It means it's in co-NP and it's co-NP hard.
and
So-
the language between OMP and NP at the same time.
Yes.
Well,
It's for homework. You have to give such a proof that for such a language, like small factor language. It's an important language for cryptography. And so I think the hint says so. Otherwise, I'm giving you a hint now. I forgot a little bit. Okay. And now notice that L is NP complete. So again, over sigma. If and only if complement of L is co-NP complete. So hereby it's true. So it's kind of simple lemma. L is NP complete over sigma if L over sigma is NP complete. If and only if complement.
by definition.
Well, okay, so it belongs to NP. By definition, complement belongs to co-NP. And so you use a property of reductions. So you use that A reduces to B if and only if complement of A reduces to complement of B.
Oh, and from there will give a completeness.
Yeah, so this by definition of reduction, and so these are two are equal. And so corollary of this is the following problem. Like always one. Yeah, given a circuit, check whether the output is given a circuit, check whether the output is always 0. So that's the opposite of circuit set. And so this is a co-NP complete problem. And so that okay, I should stop. But the problem whether NP intersects co-NP equals P. So this seems to hopefully difficult problem. But also whether NP equals co-NP. Most people think answer in both cases is not. So this is also an incredibly hard problem. Because what does it mean? That if the answer is no for a problem in NP, we can also give a certificate for it. So this is a huge open question. And so, for example, given two circuits, to give a certain, so people would be interested to have a certificate that proves the two circuits compute the same. For people who work on CPUs and so on, there is always engineer that claim to compute the same thing with smaller and faster circuit, but then the boss wants to have a proof that these two circuits compute the same answer. There are no errors, and such a proof in general cannot be made. But if you're lucky and in practice, it can be made. So he can make computer proof that both circuits are the same, and in reasonable time you can check that this proof can be checked in reasonable time. So it's kind of a very important problem, and it's also a very important attack on P versus NP problem, because if P equals NP, then co-NP equals NP. So because P is closed under complement, yeah.
So if it's not true, then P is not equal to NP.
Yeah. So if you can prove, if you can come up with a problem in NP for which no answer requires huge circuits, then you proved P not equal to NP.
Great task for coursework.
Yeah, of course, yeah. Okay, so that's it. So I will tell Nikita to only start at 7:50.